Hi, my name is Brandon Patterson. I'm a mechanical engineering student at the University of Michigan, and I use computers to study how bubbles collapse and explode in people. Okay, so explosions in people. First off, some of you might be thinking, that sounds kind of scary. That sounds like the kind of thing that could break us. And what I want to tell you is, this can actually be a very good thing. Sometimes there are things inside of us that we don't want there, and that's bad. And if we can use carefully controlled explosions to break these things up, that could be a very good thing, and it could help us out a lot. I mean, we think about cancer. Over 10,000 people die a day on average worldwide of cancer, and that's tragic. And most of us probably know someone in our lives that's been affected by this terrible disease. But if we could break apart some of these tumors using carefully controlled bubble explosions, there's a lot we might be able to do in order to help people. And I think that's great. And I want to explain to you what I've been working on with this because I think it's really fascinating, this idea of what's going on when you use ultrasound to cause bubble explosions in people. And I want to explain to you what I've learned over the last few years working on this. So in order for me to do that, we have to start from the beginning. We have to start with sound. And the first question we have to ask is, what exactly is sound? And the simple answer is, sounds are vibrations. So, when I'm speaking to you, what's going on? Well, if you speak, sing, or hum, put your hand on your throat. Any sound you make, you can feel vibrations in your throat. And that sort of thing's great. What's going on there, though? You've got little string-like structures in your throat, your vocal cords, and they're shaking back and forth very rapidly like guitar strings. And as this is happening, they're impacting the air. And these vibrations, you can think of them as pushes and pulls and pushes and pulls. And so what's happening is every time this thing vibrates, it's pushing and pulling on the air. And this causes the air to run into the air next to it, which runs into the air next to it, which runs into the air next to it. And in this way, these vibrations or sounds travel outward. And eventually they get back to our ears. And once they're inside of our ears, they push and pull on these little hairs inside of our ears. And when they do this, our brain says, hey, there's a vibration in my ear. I know what that is. That's sound. And there's a little bit more to it than that. See, there's different kinds of sound. When we talk about sound, we talk about pitch. And you have low pitch sounds down here. And these are caused by very slow vibrations. And you have high pitched sounds up here. And these are caused by very fast vibrations. But what can happen is you can have vibrations that are so fast, so close to one another, that our ears can't actually recognize them. Our body doesn't have time to really know that's there. And what happens then is we don't hear this sound. Any sort of vibrations that are too fast for us to hear, that's what we call ultrasound. When you have ultrasound, a lot of you might be thinking, I thought that was something we used to take pictures of babies. And you're right. Ultrasound is great for medical imaging of all sorts of different kinds. We can image not just babies, but all sorts of different structures inside the body. And the way this works is we send these vibrations into the body, these very fast vibrations, and they travel the same way sound does through air. Tissue runs into tissue, runs into tissue, and eventually these waves bounce back once they run into something. And when they do this, they spit out a picture that looks like this. And this is an incredibly powerful thing. I mean, many of you out there may have been seen for the first time by your parents using ultrasound. Many of you that are parents may have seen your children for the first time using ultrasound. And it brings together people. It's really pretty wonderful. But one thing I want to get across today is the idea that ultrasound is for more than taking pictures of babies. It can be used to treat diseases and injuries. It actually turns out that the idea of using ultrasound for therapeutic purposes isn't new. It's something we've been doing for quite a while. It's been shown that ultrasound can help speed the healing of lots of different kinds of wounds and can help open up the blood-brain barrier so we can get chemotherapy in for brain cancer where we otherwise couldn't. And we can break apart blood clots and gallstones and a lot of other different things. One great example of something that we actually practice already in medicine today is a process called lithotripsy. During this procedure, ultrasound waves are used to bombard kidney stones in such a way that it causes bursts of energy, shock waves inside of them, and it vibrates the kidney stones apart. Because the stone is broken up, the body is able to remove it naturally through the urinary system. This means that the doctor doesn't have to cut inside of the kidney in order to remove the stone, and this greatly reduces the risk of infection. But like I mentioned earlier, there's a lot more we can do with ultrasound. We can't just break apart kidney stones, but it looks like we can break apart all sorts of different soft tissue if we want to. Muscle, fat, tumors. But in order for this to happen, we don't just need ultrasound. We actually need ultrasound to hit bubbles. That's why I've spent the last few years studying what exactly happens when ultrasound hits bubbles in the body. So I'm really interested in this idea of bubbles and ultrasound interacting with one another in the body. I'm really curious about how the bubbles can collapse and explode in such a way that they can carve and erode away at different kinds of tissues. And it's the sort of thing that I've been studying for the last few years, trying to figure out what's going on with this. And there's a lot of different questions. One of the things you might be wondering right now is how exactly are there bubbles inside of me for someone to hit with ultrasound? And you probably know that there's bubbles and gas pockets in your lungs and in your intestines. But what you may not know is that you can actually use ultrasound to create bubbles where there weren't any before. Remember earlier I talked about how sound and ultrasound were systems of pushes and pulls and pushes and pulls? The idea is that when you have that ultrasound pull, it can pull that tissue apart and it can rip tiny holes in it. Now, I don't want to worry you. The picture I showed before, this one, these bubbles are not to scale. This is not representative of what exactly is happening. The bubbles that we create through this sort of process with a powerful ultrasound are very, very small. They're not like the bubbles you blow or the suds in your sink. You're getting a little bit closer if you think about the bubbles in your champagne or your soda. But a lot of these bubbles are actually a fraction of the width of a typical human hair. And once we have these bubbles inside of us, what can happen when they get hit with ultrasound is really fascinating. So in order to get a better idea of how bubbles behave when they get hit with ultrasound in the body, I want you to think of a bubble kind of like a spring. When you pull on a spring, it stretches out and pulls back. When ultrasound pulls on a bubble, the bubble stretches out and pulls back. When you push on a spring, it compresses down and pushes back. When ultrasound pushes on a bubble, it pushes the bubble down into a little point. It collapses it down, and the bubble pushes back. And like if you were to bounce something up and down on a spring, because the ultrasound is a bunch of different pushes and pulls, it causes the bubble to repeatedly shrink and grow and shrink and grow. But what you're probably wondering is, it just sounds like bubbles shrinking and growing. That doesn't sound like the sort of thing that could break apart tissue. And it's what I haven't told you that really makes this so fascinating. What's going on is these bubbles are shrinking and collapsing at incredible speeds, over 400,000 times in the time it takes you to blink an eye. That's millions of times a second in some instances. So that means that these bubbles are smashing into the surrounding tissue very, very quickly. That means there's incredible force around them. And it also means that you've got all that gas inside the bubble, and you're taking it from some size and then you're smashing it down really fast to a tiny little point. You can sort of think of it like a crowded subway train. When you've got all those people pushing in against each other, you sort of feel the pressure, and things are kind of warm. And that's when the bubble's at its normal state. But now imagine if that crowded subway train was shrunk down to way less than half its size, and all those people were smashed together much tighter. Then things would be really hot, and the pressure would be really high. It'd be really uncomfortable. And that's what happens inside the bubble. All that gas gets smashed together to a tiny little spot. And because of that, we get incredible temperatures and pressures. The pressure is greater than that at the bottom of the ocean. And we can actually get temperatures significantly higher than those found on the surface of the sun. So it's pretty amazing what's going on there. But this sort of thing isn't the only thing that can contribute to the bubble breaking apart the tissue. When that bubble is smashed down to that tiny little point and it's really hot and it's really high pressure, it needs to release some of that energy. And in some cases, it can actually do it in violent bursts of energy called shock waves. And between all these different things, it can really break up what's all around that bubble. Okay, I don't want to worry you. This might sound like it's getting dangerous again, but it's not. If you remembered, these bubbles are really, really tiny, a lot of them a fraction the size of a human hair. And this is happening incredibly fast. So fast that this doesn't really have time to cause any extra collateral damage or heat up the area. Any one bubble can't warm the surrounding area hardly at all. I want to share with you a video created by another group here at the University of Michigan. And this is a video of sort of what I've been talking about, this idea of bubbles carving away at tissue. This was created by Charles Kane in the Histotripsy group, and I want to give them a lot of credit and thanks for letting me use this. And what you see here is you've got a bunch of tissue, and in the center you've got these dark spots, and these are the bubbles. And I want you to watch what happens when they crank up the ultrasound. You can really see that it carves away at that tissue. We'll watch it again. Okay, so the video I just showed you of the bubbles carving away of tissue, again, that is not my work. That was done by another group here at the University of Michigan. But that is the sort of thing that I'm interested in. I'm interested in all sorts of different bubbles and ultrasound interacting in the body problems. And what is it that I do in a typical day? Well, most days, I'm sitting inside a lab and I'm thinking about my bubbles and my tissue. And the way I think about these things is I try to think of them in a mathematical context, using some pretty basic ideas, the idea that matter and energy can't be created or destroyed. We can actually use math to come up with a system of equations that describe these bubbles getting hit with ultrasound inside the body. Now, these equations would be very difficult and tedious for me to solve by hand, so together with other members of my lab, we write computer code to do it. And when the codes are done, ideally they spit out pictures and videos of bubbles collapsing and exploding in something like tissue. Now, the problems I solve, I admit, are much simpler than the actual physical problem that we showed here. But they are the sort of thing that I'm interested in. And there's a lot of things that these computer simulations are really useful for. Because this procedure happens so fast, there's a lot that we can't see inside the body when we do this sort of thing, even with our fastest X-ray cameras. So using our computer simulations, we can gain insight into things like the stresses that the body feels when we do this, and what might be causing that tissue to break up. And I'm really excited about this. I think it's really interesting. But I want to say there's still a lot of work that needs to be done. There's a reason this isn't out in every hospital being used every day. But we are constantly making strides forward. Every day there's a little bit more progress. There are doctors and clinicians and physicians and scientists all working on different problems like mine. But together, we hope that someday in the near future, between my research and all the similar research being done, we can put these things out into the real world so that they can be used to help people. But until that day gets here, I'm happy to sit in my lab, tinkering away on my computer and playing with my bubbles. All right, again, this has been Brandon Patterson with the University of Michigan. Thank you very much for watching, and I hope you enjoyed my talk.